very excited to welcome, virtually welcome Lucas Laurindo to give today's seminar. Lucas did his PhD at University of Miami and then recently completed a postdoc at NCAR and just transitioned back to an assistant research scientist position at University of Miami. So he's just made that transition in the last month or so. And he's going to talk today about the role of the ocean and atmospheric variability in air-sea interactions and scale-dependent air-sea interactions. So this will be, I think, a perfect seminar to sort of bridge our community in terms of our atmospheric representation and our physical oceanographers. So I will monitor the chat. If you have any questions, clarification questions, just send those in the chat. We can communicate those to Lucas during the talk, and then after the talk, I'll do the same thing. So Lucas, go ahead and take it away. Thanks.
Yeah. Thanks so much, Jack. Thanks so much for inviting me to present my work here. It's quite an honor. I did this work while I was a postdoc at NCAR, and I would like first to acknowledge my co-authors, Justin Small, Dwayne Thompson, and many others. And yeah, let's go ahead with the talk. Okay. In climate dynamics, it's usually considered that most of the sea surface temperature, SST variations in the exotropics is driven by weather via surface turbulent heat fluxes. However, in the past few decades, it has become clear that the ocean currents can also produce SST anomalies that are large and persistent enough to have an impact on the surface heat fluxes. And there's also increasing evidence that the influence of the ocean mesoscale processes on surface quantities can play an active role in weather and climate. And so the main goal of this study is to determine the relative contributions of the ocean and the atmosphere for driving variability in SST and THF as a function of time and space scales. So a brief overview of how each medium influences the variability. At mid-latitudes, the atmospheric variability is often organized in space in forming large-scale modes, such as the Pacific North American and the North Atlantic oscillation patterns. The temporal characteristics of the atmospheric variability are not well understood, but they are chaotic and they are often modeled as a white noise signal. Exemplify a white noise signal here in Penaway is essentially, sorry about that, it's essentially a signal that has the same variance across all scales of the motion. And in the 70s, Klaus Hasselmann and Claude Fleming presented the stochastic climate model theory, which was developed to explain how this chaotic atmospheric forcing could generate slow climate scale variations in SST. Essentially, the ocean mix layer receives this input, and due to the large thermal inertia of the mix layer, it integrates this white noise signal input to yield a red noise response in SST. By red noise, I mean that it produces an SST signal with more energy at low frequencies. And panel B here exemplifies this type of response for considering a 500-meter deep ocean mix layer. And you can see here that SST variations on the order of a few decades. And this theory was very successful to predict some critical aspects of the mid-latitude SST variability. And this includes the shape of the power spectrum of SST, which I'm exemplifying here in Penaway. This is actually from their original paper. And this is called a red spectrum, where the variance increased towards lower frequencies. The theory also predicts the linear relationship between SST and the surface turbulent heat fluxes, which I'm showing here in panel B. Sorry, again, as I said, the controls are here a bit too sensitive, and sorry if I keep flipping back and forth between slides. Anyway, you can see here, this is from a recent paper by Stuart Bishop. And when you have the atmosphere driving the variability, you form an axisymmetric lag correlation between SST and turbulent fluxes, where the correlations are close to zero, at lag zero, and are maximum of at a lags of a few weeks or so. And you also have a strong negative correlations at lag zero between the SST rate of change, which is known as the SST tendency, and THF. And indeed, before the 2000s, these were the relationships, statistical relationships that usually obtain in observational data and in couple model simulations of the time. And here, these panels are showing the correlations at lag zero, obtained at a 1 degree model resolution, obtained by a global climate model, the CESM. And panel A shows near zero values between SST and THF at most of the exotropics, while in panel B, it shows negative values between the tendency, SST tendency and correlation. And according to the stochastic climate theory, this is evidence that the atmosphere drives the variability in SST and in the heat fluxes. However, after the year 2000 or so, around the turn of the century, we had new satellite observations, in particular obtained by microwave sensors that could see through clouds, which received that mesoscale ocean features in SST could also modify near surface quantities, such as surface winds. To exemplify, this is a paper that's showing a composite of eddies detected in the Southern Ocean, composites of SST, and you can see there's a signal of SST sitting on top of the eddy. And coinciding with the signal, you have also an anomaly in wind speed. And these modifications in the boundary layer could lead to convergence and divergence in the surface winds, which could produce vertical motion within the boundary layer and even into the troposphere. So here it's a map of SST for the Florida current and Gulf Stream. You can see the SST pattern in here, and the panel on the right shows the modifications in the wind stress curve that is associated with this SST signal. And these are just different figures. This is again like eddy composites, but showing that sitting on top of the edge, you also have anomalies in the cloud fraction in rain rate. And here is from a classic paper from Minobi in 2008 that shows that the convergence and divergence pattern associated with the SST modifications, which affects the rain rate and the associated vertical velocity associated with the Gulf Stream. Anyway, by the time, the community was also able to run coupled simulations with higher resolutions in both the ocean and the atmosphere. And these simulations showed that, indicated that you can only resolve this type of influence from mesoscale ocean processes when you have enough resolution to directly resolve mesoscale eddies in these simulations. And when you have a high resolution simulation, the correlations between SST and the surface heat fluxes also change relative to a low res or standard resolution run. Here is a similar plot that I showed before, but for a CSM simulation with a 10th of degree resolution in the ocean, which is eddy resolving. And you can see that now panel A shows strong positive correlations at regions where you have strong current systems, such as the Kuroshio and the Gulf Stream and the ACC, a good certain current, etc. While the negative correlations between SST tendency and THF, they diminish, go to close to zero at the same regions. And recent studies try to extend the stochastic climate theory by Frankenau and Hasselmann to account for the influence of internal ocean processes. And like the weather, they try to represent the action of mesoscale eddies as a white noise, a stochastic process. And when they did so, they showed that the statistical relationship between SST and the heat fluxes that emerge when the ocean forcing is strong are distinct from those that you obtain in the atmosphere-driven case. Now you have strong positive correlation between SST and THF like 0, and you have an axisymmetric lag correlation between SST tendency and THF with near 0 values at lag 0. The same recent studies also show that these relationships has a strong dependency on the spatial scale. And here I computed those myself from a high resolution CSM run. And these results for correlations between SST and THF. And this is just straight up time domain correlations. And in panel B here, I used spatial filtering to remove variability with scales smaller than 10 degrees. So I'm retaining only the large scales of the variability. And note that we end up with a map that's very similar to that produced by a low-res simulation. The correlations go to almost 0 in the exotropics. In contrast, in C, when we do the opposite and remove the large scales, we now obtain positive correlations almost everywhere in the ocean. Now there are similar estimates, but for the SST tendency and THF. And when we remove the large scales, we again obtain a picture that's similar to a low-res run, with the values becoming more negative in most locations. While in C, for the small scales, the ocean mesoscales, we now obtain 0 values almost everywhere. And these results indicate that the atmosphere controls the SST and heat flux variability at large scales, while ocean processes dominate the variability towards small scales. However, these previous studies did not constrain well the scales where one coupling regime gives way to the other, nor which are the time scales of each one. So that's where my work in this research is situated. The main objectives are to determine the influence of ocean atmosphere for drive the variability, and also try to give physical insight on the mechanisms that control the scale dependence. And for that, we use spectral methods to characterize the SST and heat flux variability and how they are linearly related with each other across a wide range of spatial temporal scales. And we also use a stochastic model similar to the one proposed by Frankenau and Hasselmann to interpret the contribution of the ocean and atmospheric process to the observed spectra. So, okay. Let's go over the methods first. I use 2 CSM sets of CSM simulations. One is low-res, which I'm calling LR, with a 1 degree resolution in the ocean and the atmosphere components. The other is high-res, HR, with 1/10 of a degree in the ocean and a 1/4 degree in the atmosphere. They are both pretty long. LR has 480 years of monthly outputs, while HR has 163 years. And I also compare their outputs with 26 years of satellite observations from the JO4-3 satellite project. I use these data sets to compute the power spectra of SST, heat flux, and their cross spectra as a function of zonal number and frequency. And I compute my results at each latitude of a basin mask, of this basin mask showing this map here, for the for the Pacific Ocean. So I obtain estimates at each latitude within this mask. And to help interpret those this spectra that I obtain, I use a stochastic model describing the SST evolution. Was a modified version from a stochastic model presented by Frank and Yu et al. 1998. Anyway, this model is forced by the noise terms Na and No, which represent the action of internal dynamics in the atmosphere and the ocean. And it is composed by a turbulent heat flux term, which encloses the atmosphere forcing term, and by a radiative damping term. The way I go about this, I solve this model for the Fourier transforms of SST and heat flux, and I obtain analytical solutions for their power spectrum and power spectrum of SST, power spectrum of turbulent heat fluxes, sorry, in their cross spectrum. And all the solutions, they depend on the noise terms Na and No. And previous studies use white noise to represent these terms. But here, I wanted to use noise with a realistic variance distribution in spectral space. And the reason for that is that I wanted to check for the present, if the fact that the noise has a structure is not, and it is not purely white, if this characteristic could explain the scale dependence of various interactions. And to this end, I decided to define the noise using data obtained from the CSM simulations. So I chose to use 2 meter height humidity for Na, because we found that was not strongly correlated with mesoscale SST anomaly, so potentially would reflect more the action of internal atmospheric processes. And we use ocean heat flux conversions for NO, because we know that it is the primary driver of the mesoscale SST variability. So essentially, I compute the Fourier transform of the signals and plug them into the stochastic model analytical solutions that I showed in the previous slide. And I then adjust the noise variance to the correct magnitudes by fitting the solutions of the stochastic model to the SST and heat flux spectra from the CSM runs. Yeah, anyway, the figure in the slides show the power spectra of Na, which I call geophysical noise spectra for the atmosphere, and then O for the ocean as a function of zonal wave number and frequency. And note that they are not purely white, they show structure. The atmospheric noise is approximately white with the same power in frequency space, but it is strongly red in zonal wave number space with much more variance at large spatial scales. And you can see that the ocean noise is a bit different. It's also red in wave number space, but it shows more variability near the dispersion relation for first mode Berkeley and Rossby waves, which are represented here by the black lines. Okay. Okay, so let's go to results. Before start showing the spectral estimates, I'll start with these global maps showing just the straight up monthly variance for the variance ratio for between the high resolution run and low resolution run, top panel for SST, the bottom panel for the surface fluxes. Note that I removed the seasonal cycle from the data before computing those maps. And note that both maps show that the high resolution run results much larger variances. It's much more variable in SST and THF than the low res in most of the exotropics, and notably coinciding at energetic ocean current systems and large-scale SST fronts. Note that the color scale here is logarithmic, meaning that a value of 1 indicates that HR, the high resolution run, has 10 times more variance than the LR. And these maps are also very similar to each other. So this is consistent with the interpretation that in HR, SST variability driven by ocean processes is forcing a response in the turbulent fluxes. Okay, now the slide shows the power spectrum of SST. I will not show the results for turbulent fluxes because they are visually very similar to this one. And this type of representation is useful to show at which scales these excessive variance in the high resolution run are contained relative to the lower S. So the first panel here show estimates for 40 South in the Pacific. The black lines for observations, the blue is for HR, and the red is LR. The scale here goes from about 7,000 kilometers wavelengths to 40 kilometers. Note that all data sets have similar variances at scale larger than 2,500 kilometers, but as you go towards smaller scales, the variance remains high in HR and in observations, while it just keeps diminishing in LR. Panel B shows the ratio between the power in HR and LR, this time as a function of latitude. The results that I'm showing in panel R are marked here in as a black line. This is also in log scale, so value 1 indicates that variance in HR is 10 times larger. This type of plot here shows that the larger variances in HR occur at most latitudes in the extratropics. And for reference, these dashed lines here, they represent the Rossby radius of the formation in the atmosphere and in the ocean. Note that the most significant difference between HR and LR occur at scales that are smaller than atmospheric, the atmospheric Rossby radius. Now, this slide shows the corresponding estimates, but obtained using the stochastic model. So these are obtained using the analytical solutions, representing estimates for HR on the left in panel A and LR on the right. The gray lines here, the thick gray lines, are the power spectrum computed for CSM data. The blue lines are stochastic model estimates that obtain just noise in the ocean, while the red lines are estimates obtained using atmospheric noise. The black lines that you can barely see here are the sum between blue and red. And in panel A, we can see that the atmosphere-driven component is significant at large spatial scales. However, its power decreases steeply as you go towards smaller scales, a characteristic that allows the ocean-driven temperature modulation to become larger than that of the atmosphere. And note that this happens at pretty long wavelengths, close to 2,500 kilometers in this case. While in panel B, we see that something similar occurs in LR, but the ocean-driven component is much weaker, while the atmosphere-driven part has about the same magnitudes as in HR. Now I'm showing the cross-spectral statistics between SST and refluxes as a function of latitude. Cross-spectral statistics is just statistics, but solved in spectral space. So that allows us to figure out how the signals are linearly related with each other as a function of different wave number or frequencies. And panel A shows the coherence, which quantifies how SST and the heat fluxes are related. This quantity, if it is 0, it means that both quantities are totally unrelated. And if it's 1, it means that they are perfectly matched, they vary together with each other. While the bottom panel shows the phase factor, which measures the phase relationship between both signals. So, okay, at large spatial scales, we see the weak coherences associated with 90-degree phase. However, as you go towards smaller scales, the coherence increases while the phase goes to 0. Means that they are when temperature is high, turbulent flux is also high, and they are phase locked, like positively correlated. While at large scale, since they are in quadrature, it relates more to that lag relationship. They are related, but the relationship at lag 0 is weak. And now in this slide, I'm showing the corresponding results for HR and LR. We can see that HR is very similar to what we obtain in observations, while LR does show similar characteristics at large scales, but it cannot resolve this band of incoherences that's present in observations and the high-res run. In LR, note that it shows slightly larger coherences near 40 north, about the latitude of the current extension, and in the tropics, also coincide with smaller phase angles. So here, it seems that LR even tries to do something similar to HR knobs, but the signal is much weaker. And here now I'm showing the corresponding stochastic model estimates. Panels A and B shows the combined effects of both ocean and atmospheric noise. I'm masking latitudes smaller than 15 degrees because this stochastic model is not valid near the equator. But you can see that these results are similar to satellite and the high resolution results. And we can separate the influence of ocean noise and atmospheric noise. And when we do so, we confirm that this band of incoherences reflects the action of ocean processes, while the characteristics at large scales arise from the action of the atmosphere. I showed before the results as a function of zone wave number. Now I'm going to show results obtained as a function of frequency. So starting again with the SST and turbulent heat flux spectra. These estimates are for 40 south in the Pacific, just for the HR run. Panel A shows the estimates for SST, while panel B shows estimates for the turbulent heat fluxes. Again, the gray lines are the original spectra from the CSN outputs. Blue is just the stochastic model estimates for obtaining using oceanic noise, while red is for the atmospheric noise. And starting with SST, we can see that oceanic noise produce a more substantial variability at periods shorter than about 500 days. And as you go towards longer periods, the variability induced by the ocean and the atmosphere, they become more or less comparable, although the atmosphere-driven component is stronger in this case. In any case, you can see that both the ocean and the atmosphere, they produce stronger SST variability at lower frequencies. They both produce a red spectrum response. It is well known that the atmosphere drives this kind of response, as I showed in the beginning of the presentation, but here we find evidence that ocean noise can also do something similar. And when you look at panel B, at the heat fluxes, we find the opposite, like that the atmosphere controls most of the variability at higher frequencies, while the ocean controls the variability at lower frequencies. And to double check our conclusions on the influence of ocean processes, we can filter out the large scales and recompute the results. And when we do so, we note that the now obtained spectra with very similar shapes, with the stochastic model results indicating that the ocean predominantly drives the variability here. Now I'm showing the estimates of the cross-spectral statistics. This is panel A is the coherence between SST and THF, predicted by the stochastic model. This is also for a spatial scale smaller than 1,000 kilometers. And they indicate that SST and THF, they remain coherent and in phase over the entire analyzed frequency range, which goes up to about 80 years here. Anyway, this stochastic model confirms that the highly coherent signal arises from the action of ocean processes. This is my last slide of results. It's also showing just the coherence, but panels A, B, and C shows estimates for the entire latitude range in the Pacific for observations, HR and LR. And you can see again, like this observations in HR, they are very similar to each other, although the signal seems more coherent in HR than in OBS. And if you look at to LR, it looks like all noise, like the signal is much weaker than in observations in HR. And at the bottom here, those are the corresponding stochastic model estimates. Panel B here shows the full solution, including both oceanic and atmospheric noise. And when we break it down into ocean influence of the ocean and the atmosphere, you see that this band is all driven by ocean processes. So, okay, the conclusions of this study, at mid-latitudes, we find that the atmosphere dominates the SST, double entity flux variability at spatial scale smaller than 2,000 kilometers. In the high-res run in observations, ocean processes control most of the variability at scale smaller than 2,000 kilometers. And we find that it can prevail at these long scales because the ocean forcing remains strong, is strong at the scales, while the atmospheric forcing has the steep slope, so it's much weaker than that on larger scales. We find that the atmospheric Rossby radius of the formation seems to be a relevant scale to control the transition between atmosphere-driven and ocean-driven variability, although we still don't have an explanation of why that is the case. We also find that ocean processes can drive oscillations in the SST, which are mirrored in the heat fluxes from intraseasonal to multi-decadal timescales over much of the exotropics. And finally, we find that the influence of ocean processes in the low res is much weaker than implied by the satellite and high-res results. We really have a gain in realism when you go high-res. And that's all I had. Thank you so much. In the screen, you can see my email if you want to get in touch later. And also the reference for the paper on this study. Thank you very much.
Thank you, Lucas. If we have any questions, you can go ahead and unmute yourself or put questions in the chat. Edmund, do you want to go ahead?
Yeah, thank you. Can you hear me?
Yeah.
Sure, yes.
Hi, it's a nice talk. Thank you. Very interesting results. So you just showed these results, but you didn't really discuss what the implications of this result are. So compared to high resolution versus low resolution, so this is obviously very different. The oceanic control of the smaller scale interaction. So what is the most important implication? So what, for example, what kind of bias that in the current climate models would this would depend on this interaction, and using high resolution might help alleviate those biases?
What I can answer from my results alone is that if you when you go to high res, you resolve a much larger SST variability and heat flux variability. These quantities are much more variable in the high res than the low res run, and is also closer to what's shown by observations. We also show that if you have mesoscale ocean variability, even though like the scales of the mesoscale eddies are fairly small themselves, they can also affect the variability of this, like influence the atmosphere over pretty long wavelengths, very long time scales, just like weather can produce variations in SST with time scales of decadal to up to decadal, according to the simulations. About implications, I cannot say much beyond that based only on my results, but there's plenty of other evidence that from other studies that if you have high resolution if SoMAS scale edits and in a coupled simulation, you can have an increase of predictability, although you also alleviate biases in precipitation. And yeah, but I think we still need to do a link between, okay, how to link those results to, okay, how does this lead to high predictability, for instance.
Yeah, thank you.
Christopher, did you want to ask a question?
Sure. Could you go back to the slide where you were showing the stochastic model,
Sure.
the sort of pen and paper one? Okay, yeah. So this is what I was a little confused about, because you showed results that had like a dependence on wave number, and I was trying to, oh, you've got, so are these L's wave numbers? I was just trying to figure out how the wave number got into this equation, because it's just it doesn't have speed.
Yeah, it does not. The model itself, it's only depends on time. It does not have an explicit dependence on wave number. These LK and LW is just the size of the domain, so it's just a number. It's not dependence on K itself. The idea is that was to see if just the dependence of zonal wave number comes from the noise. You know.
So you specify some sort of spatial correlation scale for the two noise terms, and that's where that comes from.
Actually, I specify directly the noise, you know. So when I'm showing this in panel A and B, it's actually the power spectra of the noise.
Okay, okay, and then you forced your stochastic model with this spectrum. Okay.
Yes. Yeah, so it's essentially all I do, I plug in this this spectra to the stochastic model and compute the solution.
Okay.
And yeah, like since the model does not have any dependence on K, this dependence can only come from the structure of the noise. You know?
Okay. Cool. Makes sense. Thank you.
Sure.
Lucas, would you mind going back to your spatial plots where you show the plot of SST variance?
Sure.
Variance ratio. So obviously there's a lot of structure along the basins. I was just so in your analysis, were you doing averages? So you're doing plotting by latitude. Were you just averaging across the basin?
Yes, yes. So I do not distinguish between. It's just an average across the whole basin. Yes.
Yeah. So have you done any analysis or looking into some of these spatial patterns? Right, like you're obviously seeing huge differences in sort of eastern and western boundary current systems, and have you done any analysis into that?
Yeah. I did, and you're right. You, especially if you go to the Kuroshio or Oyasho, you have much more variability there.
Mm-hmm.
And I did try to just separate the eastern and eastern parts of the basin, but the results are very similar. And why is that? Like, what changes is the like, because the physical mechanisms, they try to separate by scale, you know. So let me go here. Here, this is for 40 South, so a very quiescent region of the ocean. But still, like if you go to the Kuroshio, you still see the same kind of structure, you know, but you're gonna have more variance. Like these curves are just bumped up, you know. But the biggest difference between low res and high res is still gonna be in this wave number range here. So yeah, and the reason for that is that even you're looking at quiescent region of the ocean, you still have a lot of eddies, you know, and you can distinguish the action of them, their action, from the scales that they're acting, you know. They're not evident if you just compute a straight up correlation, because like a time domain correlation, because when you compute a time domain correlation, you are mixing all scales of motion, you know. And in that case, you're going to have much more variance and covariance at the large scale band where the atmosphere dominates. So when you compute just a point correlation there, then the statistical relationships more suggest, oh, atmosphere is larger, the influence of the atmosphere is larger here, but that does not mean that the ocean cannot have an impact as well, you know. That's why one of the takeaways that that from this from this type of work is that you need to expand it. Like the advantage of using spectral methods is to recognize the different processes that are occurring at different scales. Sorry if I was.
Jack, I had a question. This is Malcolm. In the ocean, the anticyclonic eddies tend to be buoyant, so you see them at the surface, but the cyclonic eddies tend to be heavier and sink, and you don't see them. So, like in the Sargasso Sea, is full of cyclonic eddies as well, but they're deeper down. So, how would that affect your analysis?
Let me think. I don't know. Like, I'm guessing. Try the variability. If you can see the yeah, like when you do the spectral analysis, it's actually a big blender. It'll just throw all the signal that you have there. So if you have like this asymmetry in the surface expression, I don't know, I guess would just appear as the influence of the eddies would just appear as deeper negative anomalies than the positive anomalies. I don't know how to answer that, but I don't. Yeah, I just throw everything in the spectral analysis, and I cannot really separate this type of cases, I guess.
Thank you.
Can I ask you a question, Jack?
Yeah, go ahead.
Sorry, I can't raise my hand. And
No problem.
so, Lucas, this is almost like a follow-up to Malcolm's question. You showed how the Gulf Stream and the Kuroshio kind of affect these convergences in the atmosphere, the wind, and I just wonder if this method is able to pick up. I didn't see any traces of the influence of storm tracks. You know, I'm trying to flip it the other way around, like for the atmosphere. Why don't we see signals of the storm tracks?
Yeah, I showed here those modifications. There are modifications in wind. I'm not looking at wind in this wind, the precipitation, clouds. I'm not analyzing those quantities in this work itself, but instead I'm just looking at the first impact of the mesoscale features, SST features has in the atmosphere, which they produce anomalous heat fluxes associated with them. And from that initiates all these modifications within the boundary layer. And the type of statistical relationships in spectrum between SST and turbulent heat fluxes, they are essentially local, you know. So
Okay.
so like if you have like mesoscale eddies in the crucial and that have some downstream effects, modifying the storm track and all that, that is this type of analysis does not
I see.
is out this type. It's essentially just show where the ocean can force the atmosphere.
Right. I see that. Thank you.
Sure.
Any more lingering questions? Okay, if not, thank you so much, Lucas, for presenting today. This was great. And if there's anyone who's interested in meeting with Lucas, he still has a little bit of availability this afternoon. So just let me know if there's interest there. Otherwise, everyone have a great day, and thank you again for joining us, Lucas.
Thank you so much. This was really cool. Thank you.
Yeah.